13. This is the beginning of the last unit where we are doing mechanics. And chapter 13 is gravitation, then we're going to do simple harmonic motion. But let's stick to chapter 13 for now. The packet starts off with a review of Newton's laws of motion. They're important, so know them, obviously. Types of forces, we have gravity. Weight, we usually talk about weight as your weight on a planet, so mg, that kind of thing. The normal force, Fn. Centripetal force, again, don't forget, that is a net force. It's not one of the fundamental forces, right? You never draw centripetal force on a free body diagram. And so we have example 1. You have a force of attraction between two bodies. What is the force of attraction if one of the masses is doubled? Well, if you double one of the masses, then you double the force. So F is 2F. If one mass is doubled and one mass is tripled, well then in that case, it's 6F, 6 times the original force because the masses have increased by that much. We're going here by G_mm over r squared using that. So m times m, 2m times 3m gives us 6, so times 6. And then see if one mass is tripled and the distance between them is halved. So in that case, right, so you should see this is G 2mm, or 3 rather, over 1/2 r squared. This becomes 1/4, and then 4, so it's 12 G_mm over r squared. And so you get 12 times the original force for part C of that question. Gravitational force due to extended bodies. Right? This really applies, G_mm over r squared, that applies to point masses. For extended bodies, the rule is we have to add up all the forces from each of the individual particles. And how do we do that? We do that by integrating. Right? And you can see how it's set up there. M, what's the mass on that particle due to that extended rod that's next to it. And so we can find that by doing this. We have lambda, remember that's the linear mass density, and that is m over L, or dm dl, or in this case we're going to call it r because of the way it's set up, dm dr. And so then dm is lambda dr. Okay. And so F is we're adding up all of the little forces that are there, and that's going to be from R initial to R final of Gm. This is the mass of the point particle m. It's over there. Gm over r squared dm. This is the gravitational force on that particle from each of the little individual particles in that extended rod. But dm, we know, is this. So this is going to be from r initial to r final, G m over r squared lambda dr. And so when I do this, let's see. Oh, and lambda is m over L. Right? So we go the next step, Ri, Rf, Gm m over Lr squared dr. Now we take the antiderivative. One way of doing this is using the quotient rule that I think you've learned. But if you think of this as a r to the -2, just kind of put it up here, r to the -2, then you can use the power rule just with a negative. And so what we end up with is Gm m over Lr negative from Ri to Rf. And so we end up with, we have that distance d, all that stuff. So Gm m over L, and then over here we've got 1 over, let's see, L, here's the negative, so keep that L front, D plus L minus 1 over D. Right, here's the initial radius, here's the final radius is D plus L all the way out there. But we do some fancy work here with trying to simplify that, so we get G M over L. This then becomes D over D times D plus L minus D plus L over D times D plus L. And so then I have this minus this, I subtract the numerators, and I get GMM, and I have negative L here. All of this is still, I have the minus in front, right? Over L times D plus L. Those L's cancel out, the negatives cancel out, and I'm left with GMM over D times D plus L. And so that now is the formula for the gravitational force on the point mass due to the rod where it is in line with the rod. Okay. And if L equals 0, think about that for a minute. If L equals 0, then you just get D squared. Think what happens if I make that, instead of a rod, we kind of make it really small, so then it's like a point mass, and then we just end up with our other formula, GMM over R squared, but in this case D, because that's the distance between the masses. Okay. And so if we have a uniform spherically symmetric mass, that's a different thing. That's not like having a rod. Instead there, what we do is we treat the gravitational force as if that big sphere is a point particle centered at the center of the sphere. And then, let's see, the shell theorem. Shell theorem 1. A uniform spherical shell of matter attracts a particle that is outside the sphere as if the shell's mass were concentrated at the center. So you can imagine if I have a uniform spherical shell, and I want to, I calculate the distance from there to some other particle that it's attracting, I treat that mass as if it's concentrated at the center. Okay, that's the first shell theorem. So example 2, rank the forces of all masses are equal and all center-to-center distances are equal. So A, B, C, and D, they're all the same because the center-to-center distances are all the same and the masses are all the same. So whether those are shells, or they're evenly distributed masses inside, solid, doesn't matter. A, B, C, D all have the same force of attraction between those bodies. 13.3, the principle of superposition. Here we're simply saying that the force of gravity on an object is the sum of the forces from all the other objects in the system. And we're adding them up as vectors because force is a vector. Right? If I have a mass in the middle and 2 masses on either side, those can cancel each other out. It's not like moment of inertia or something like that, where we're just adding everything together. So that's important to know, that the principle of superposition. And that worked. That worked for a while. It was using that people were able to calculate and discover new planets because they noticed discrepancies with the orbits of the planets. Well, according to superposition, they used to calculate gravitational force between all the other bodies in the solar system, and then look at the orbits and they realized there are other planets out there. That's how at least Neptune was discovered. Gravitational field. All right, gravitational force is different from most forces because the masses don't have to be touching, which is still really strange, right? Isaac Newton said that this made no sense. We still don't really understand how can something millions of miles away exert force on something else. We don't know, but it does. It's crazy. And so a gravitational field, the field is the means by which 2 particles interact. The field is kind of the mathematical construct that scientists came up with to describe this. It doesn't explain it, it doesn't tell us why in the really strict sense, but it gives us a description. So we imagine bodies having these gravitational fields, And G, okay, the gravitational field is big G m over r squared. And then we have r hat. So remember we had unit vector notation with ijk? Well, we also have that spherically. And spherically, this gravitational field points inwards towards the object. Okay, so r is a vector, a unit vector that points inwards towards the center of the sphere. Okay, quick clarification on that. The r vector points away from the object that has the force being exerted on it. Actually, typically we don't talk about the r vector in terms of the acceleration. Usually we talk about it when we're getting involved in the math of the forces involved. And we're going to see that with electrostatic forces as well. So technically r points in the direction where r gets bigger. So r away from the object, but it's towards the other object, right? So if I'm looking at the force of this sphere on this sphere, then the force on this sphere points towards the center of the other sphere, right? So r points to the other object, right? So r vector gets larger as it goes away from the center of the object that you're talking about. So r is positive in the positive direction away from the object of reference. Okay, back to the lecture. Or the circle, whatever you might be using. Okay, and so we could say that the field forces are always there, no matter what the medium is that separates the two bodies. So if you have a big planet and then a star and then another big planet, those planets are still exerting force on each other, even though there's something in the middle. And so gravitation near the Earth's surface thank you. Gravitation near the Earth's surface, there is gravitational acceleration, which you know is g. Right? If you take this and you plug in g, the Earth's mass, and the Earth's radius, then you end up with 9.8 meters per second squared. And so at the Earth's surface, the gravitational force is given just by ma. You know, and a comes from this. But the gravitational field of the Earth is not really uniform for a number of reasons. One, the Earth is not perfectly uniform. Two, the Earth is not a sphere, it's an ellipsoid, right? It's spinning, it's actually wider at the equator, and the Earth is rotating. Since it's rotating, you have, you know, if this is the equator, someone standing here is on the outside, they're getting spun around. And so you've got centripetal force there as well. And so the question is then, where do you weigh the most on the Earth? Well, it will be at the pole. At the pole because that has the smallest radius. And also you're not subject to this, the fictional centrifugal force that would kind of feel like you're getting thrown outward into space. Okay, gravitation inside the Earth. Shell theorem number 2. Pay attention to these shell theorems because you're going to see them again with what we call Gauss's law in E and M. And that's pretty crazy. If you have say you have a giant planet-sized spherical shell, what would be the gravitational field inside? 0. There is no gravitational force inside of a shell. Okay? If a particle is located inside a uniform solid sphere, then the only force the only gravitational force is what is inside the radius. So you have the illustration there, but let's just take a look. Here's a solid uniform sphere. An object is located here. The only mass that's exerting a gravitational force on this is anything within the inside of this radius, r away. Anything out here is not exerting a gravitational force on this object. Okay, and so gravitation inside the Earth, again, it's not really perfectly uniform. So you can see there are these different, it changes depending on where you are. It's denser, and then as you get out, changing density. So that's going to affect the way the gravity works. However, let's kind of ignore that for a minute, and let's say how could we find the gravitational force inside of a solid uniform sphere? And so we're starting off with this. This is the beginning of our derivation. And rho is m over v, right? dm over dv if we're going to do an integral. And that's, that was the bell. And now the mass of the Earth divided by the volume of the Earth, which is 4/3 pi r cubed. We use big R to denote the unchanging radius of the object itself. That's going to be common, by the way. Big R is the fixed radius of the object. Little r is the changing radius that we're using to measure how far something is from the center. And MENC means enclosed. It's the mass that's enclosed within this radius. That, again, we're going to see that on a regular basis, so get used to seeing that. The mass enclosed, though, I can find this as a function of this. The enclosed mass is, I just bring this up here, right? 4/3 pi r, little r cubed, times the mass of the Earth over 4/3 pi big R cubed. Things cancel out. Hello, Mr. Y. Hello. Everyone say hello to Mr. Y. And so now we have the enclosed mass as a function of the mass of the Earth and the ratio of the cubes of the radii. So this is mass of the Earth, little r cubed over big R cubed. Want to say hello? Okay, and so G is gm over r squared. This is the acceleration. Except we know that the enclosed mass is going to be this. So we can put that in there. And so we end up with G mass of the Earth r cubed over big R cubed over r squared, little r squared. Because we're talking about what is the gravitational field produced by some inner radius of the object, right? So again, we've got this kind of thing. What's the gravitational field here? Well, it results only from the enclosed mass, that's this, and that is this. These things cancel out, and so it's G mass of the Earth r over big R cubed. That's the gravitational field given as a function of little r. And so that's a linear relationship, right? If we had a graph inside of a solid spherical body, the gravitational field, and this is f, or rather lowercase g, right? And this was the radius, and this was big R, the fixed radius of the thing that would go out. This looks like this. So then when you have R, little r less than big R, it looks like this. And when you have little r bigger than big R, greater than big R, then you have G mass of the Earth over little r squared, and that looks like this as you go out. So inside the radius is given by this function. Outside the radius of the object is given by this function. So now, gravitational potential energy. Keep in mind that, remember, U was negative integral f dx, or as a function because f was the negative of du dx, right? And so gravitational potential energy is given by this. U as a function of r is negative g m1 m2 over little r, sorry, not r squared, just r. And notice that it's negative. And so what's the value of r? Rather, what's the value of u when r is infinity? Let's say you get infinitely far away from some object, some massive object. what is the gravitational potential energy created by that object when you're at infinity? 0. If this goes to infinity, this thing then goes to 0. And as you get closer to the object, you have negative gravitational potential. So here's the thing. For gravitational potential energy, we set the datum at infinity. And so then this is what you're filling into the box. And then the other box below, you get this. So delta U is given by U final minus U initial, which is going to be the integral of negative R initial, R final, force as a function of R, dr. Okay, that also tells us that the force as a function of R is negative du dr. This makes sense because if I take this and I take the derivative of this, then I get the force function, gmm over r squared. Right? Okay. So now we can derive the escape speed for an object trying to leave Earth. Right? How fast would you have to shoot something off of Earth, neglecting air resistance and all that kind of stuff. Here's the idea. It's a GAPSI problem. The initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. And what we're saying here is that at the end, how fast would it have to be going to just make it to the datum? So we're saying this is 0. And at infinity, we have 0 potential energy. So that's 0 as well. So I end up with the initial kinetic energy has to be equal to the negative of the initial gravitational potential energy. Okay. And so then this 1/2 mv escape velocity is equal to the negative of u initial. Well, that's the gravitational potential energy on the surface is just gmm mass of the Earth over the radius of the Earth squared. You're going from the surface of the Earth. So this is negative g mass of the Earth times the mass of the object over the radius of the Earth. Sorry, the r is not squared. This is mv squared, of course. And so now I bring m over and multiply by 2. And so I get that v escape is the square root of, this m cancels out with this one. And so this simply becomes 2gm over r. Where m is the mass of the Earth, r is the radius of the Earth, and that's the escape speed formula. And I think when you plug the numbers in, you get something like 1.1 times 10 to the 4th meters per second. And when we're finding gravitational potential energy, one of the best ways to think of this, the gravitational field, is think of it as if you've got a rubber sheet laid out and you're placing objects in the sheet. So it creates like a contour map, right? And you can think of that as a negative as a well, right? A place where things are going to be attracted. They want to go down into that. And so if you have a bunch of things, right, in different spots, the gravitational potential energy is going to be given just as the sum of those things. Right? This is not, it's not a vector. So we just add those things up. And so then U total is simply the sum of all the individual objects. So if you've got a bunch of masses, it's going to be negative g, and then you have to look at the interaction, all the different masses that are there. And 1m over r from 1 to 2, between 1 and 2, plus m2, m3 over r 2 and 3, plus m1, m3 over the distance between 1 and 3. Right? If the system contains more than 2 particles, the total gravitational potential energy is just the sum of the potential energies of all the pairs. And so that means, if you've got two particles in a system, you have one pair. If you have a three-particle system, there are three pairs, just like that one. If it's a four-particle system, you've got six pairs. If you've got a five-particle system, you have 10 pairs. So you're just adding up the gravitational potential energy from all the pairs of objects, all those forces that are being created by all those objects. So now we're going to see how one of these examples works. We've got example one. Given these masses and these radii, calculate the gravitational potential energy of the system. And so here's G, 6.67 times 10 to the negative 11th. That has not changed. And then between 1 and 2, 1 times 2 is just 2. Distance between them is 3 plus, and then 2 and 3 is 2 and 3. And the distance between them is 4, so 6 over 4 plus, and then 3 and 1, 1 and 3, 3 over 3. And so, when you calculate all this out, it comes out to negative 6.67 times 10 to the negative 11th, 19 over 6, and then it's going to be joules. It's not calculated all the way out, but as long as you get this, you just punch that into the calculator, and that gives you the answer. Okay, verification that U equals mgh is valid. When we're doing this, what we're talking about is having, here's the radius of the Earth, and then we're talking about being some height h above the surface. And this is a real key thing. In a lot of problems, you're going to see some distance from the center, or it'll be worded some distance from the surface. Don't forget that if it's saying from the surface, you've got to add in that radius to the center in order to get the gravitational force or the potential energy or something like that. And you can see how, delta U here compared to there, but then if h goes to 0, or h is much, much less than RE, we should say, then we end up with mgh, which is our normal potential energy formula. Okay, so applications of escape speed. For A, we're looking for the escape speed for a body being projected from the Earth. Again, we're just using this formula, so G, the mass of the Earth over the radius of the Earth. And as we saw before, that comes out to 1.1 times 10 to the 4th if you're on Earth. But then being projected from the surface of the Sun, that's a different matter. So we have V escape, the square root of 2, 6.67 times 10 to the negative 11th. And the mass of the Sun, which is about 1.99 times 10 to the 30th kilograms. And then the radius of the Sun is 6.96 times 10 squared, or 10 to the 8th, sorry. 10 to the 8th meters. And when you do that, it comes out to about 6.17 times 10 to the 5th meters per second. Another application of escape speed. Here we're not using a formula, for example 3. Instead we're going to have to use gap C. So let's take a look. In this problem, you have to be careful. It says, get to a location 3 Earth radii above the Earth's surface. So that means we're going from here to then 4 Earth radii from the center. Because when we calculate potential energy, we've got to go from the center here. And so this gap C looks like this. Ki plus Ui equals, and then we just want to have UF. We want to get to here with no kinetic energy. And here we do have potential energy because we're a distance RE away from the center of the Earth. So this will be 1/2 mv squared plus gmm, I'll make this the mass of the Earth, over the radius of the Earth equals gmm over, and now we're going to be 4 Earth radii away, 4 RE. We're looking for V. The little m cancels out. Right? The mass of the body doesn't matter. And we're going to subtract this over to this side. So this is 1/2 V squared equals, let's say, 1/4 GM over RE minus GM over RE. So let's do 1/2 V squared is 1/4. So this is going to be negative 3/4 GM over RE. Let's not forget these are negative. So that's negative, negative. This is negative, subtracting a negative. And so this ends up being positive. Forget to include that. That's important. So now V is going to be the square root of, but if we multiply the 2 over here, this is 3/2, square root of 3/2 GM over RE. So if something launched at this velocity will get 3 Earth radii above the Earth's surface. Okay, for example 4, we have the Earth and the Moon. Earth is 80 times the mass of the Moon. And at some point between these two, the gravitational force is 0. These two forces balance each other out. This distance is 4 times 10 to the 9th meters, so I set this up as x. And then this is 4 times 10 to the 9th minus x. And so I just set the two forces equal to each other. The force of the Earth on this thing and the force of the Moon on this thing. Let's call this capital M, or give the mass of it as capital M. So this is G. Here we'll have 80M, 80 times the mass of the Moon, times big M, the mass of this thing, over, and then this distance is just x squared. Thought somebody was at the door. Okay, and so then the mass of the Moon, the force that's exerted there is G times the mass of the Moon times the mass of this object over 4 times 10 to the 9th minus x squared. Okay, so this big M cancels out, this little m cancels out, the G cancels out, and I'm left with this 80 equals, I'm going to write this, x squared over 4 times 10 to the 9th minus x squared. So now I'm just solving for x. One way to do that is take the square root here. So I'm going to have the square root of 80 equals x over, right, this thing is squared, right? So x over 4 times 10 to the 9th minus x. I can bring this over here. And so I get 4 times 10 to the 9th root 80 minus root 80 times x equals x. So 4 times 10 to the 9th root 80 equals x plus x root 80. And so then you add these two together. I don't know what that turns out to be. So this might be a handy time to take out the calculator. Or you could do this. This is x. 1 plus root 80 is this whole thing. So then x is equal to 4 times 10 to the 9th root 80 over 1 plus root 80. If you're trying to hit the calculator as little as possible. And when you do that, I think you get about this. 3.6 times 10 to the 9th meters. So that's how far you have to be from the Earth. And so then you're going to be 4 times 10 to the 8th meters from the Moon. Okay. And that is the end of the first chapter 13 package.